Heap sort is an improved version of selection sort. While selection sort spends a lot of time going through the unsorted section of the array, heap sort drastically reduces that time by using a special data structure. This data structure is called the binary heap, or simply the heap. The whole thing works like a binary tree, a concept similar to what we saw with binary insertion sort. And once this special data structure has been built, the heap sort algorithm now enters a new stage or a new phase. And as a matter of fact, you can see that quite nicely in our visualization, which is playing on the screen right now. At first, that is in phase 1, everything turns red and is very roughly, sorted from largest to smallest array element. Then, in phase 2 of the sorting process, the algorithm takes the largest element out of that heap, so that's the element to the very left, and places it into the sorted section of the array all the way to the right-hand side, which we can see evolving in white, or developing in white. And heap sort then updates the binary tree and again moves the largest element from the tree to the sorted section of the array, and so on. The whole thing is very interesting to look at, and it's so different to what we've seen before in the series. I hope you find this video interesting, and anyway, let's head over to the numerical example. So I'm now in a new script called heap.py, and let's have a look at the following unsorted array. It reads 2, 5, 4, 1, 3. We've seen that before. Now the first thing that we'll have to do with heap sort is to think about this array as a binary tree. What does that mean? A binary tree means that I'm splitting the data. I have one element as the root node, and then the next two elements in the array will be the two children nodes of that first root node. So in our case, this 2 will be the root node. So this will be the first node in what will be a tree, okay? Now the next two nodes, 5 and 4, will be the two and the only two children of that first node, of that 2. So if we look at this, we can position the 2 in the center here, and then we have these two children, 5 and 4. Now the next two elements in the array will be the two children of the first child of the root node. Okay, so this 1 and 3 will now go over here. So we are starting a new layer in the tree, the third layer. We have the root layer up here, then the first children layer, and now comes the next children layer, okay, the next layer of children. And here it's these two array elements, 1 and 3, that are now the two children of 5. Now there aren't any array elements left in this array to make 4 a parent by itself. So 4 will not have any children. It will be what's called a leaf node. So we've seen something similar to this with binary insertion sort, but we haven't really talked a lot about this binary tree structure in detail. So this is how we can visualize this graphically by drawing it out. So in other videos on YouTube and in blog posts and stuff like that, and I think even in the Wikipedia article, even though I'm not too sure, we will have visualizations of this. But if it's not in heap sort, you can just click on the link to the binary tree data structure within the heap sort article in Wikipedia, and you will see these nice diagrams which kind of look like this, and typically they draw little connections between the parents and their children. But this is what the binary tree looks like. Now what heap sort does, and where it gets its name from, is it sorts that. So remember, the critical thing about heap sort is that it's sorting not, well, the goal is to sort the array, yeah, that's what the whole thing is about, right? But it's kind of making what binary insertion sort did for half of the array, it's kind of doing this for the entire array. So binary insertion sort used the fact that the sorted section was already sorted, and heap sort now takes that to the next level, and on some level sort of imposes a bit of structure on the unsorted section too before it actually sorts that section, okay? So what it does is it creates a max heap. Now a max heap is created from this binary tree by, well, first copy pasting this binary tree down here. So we still have 2, 5, 4, 1, 3. And now the max heap algorithm, max heap function, we'll code this, looks at this tree and then asks, well, are the parents actually, I'm going to just say older than their children? So we'll interpret these numbers here as the age of the different nodes. And it looks at this and says, well, it's going to start with the leftmost parent, so to speak, the left downmost parent in the binary tree, which is this 5. And it then looks at this and says, well, no, actually, I'm explaining this wrong. No, it looks at the top of the tree, okay? It looks at the top of the tree and then says, okay, this 2, is it older than its children, 5 and 4? No, it's not. So there's something wrong here, and we have to make a swap. And now it's swapping these 2. It's swapping this 2 and this 5, okay? So it makes this correction, and now the first layer, the first level of the tree reads 5, 2, 4, and now the parent is older than both of its children, and that's perfectly fine. And now the max heap function goes to the next level, and it now looks at this subsection of the tree. Now it looks at this 2 and compares it to this 1, so this makes perfect sense. The parent is older than the child. But now, if we are looking at 2 and 3, no, that's not right. So here, the child is older than the parent, so we have to swap this, and this gives us this structure over here where now these constraints are all satisfied. So we have the root node of age 5, and then we have 2 children of age 3 and 4, and then another 2, which are sort of the grandchildren of this root node. And anyway, these grandchildren are of age 1 and 2, which is less than 3. So now the array, if we sort of put this tree back into the typical array form, we start at the root node, take the left child, the right child, and then the next level, and so on. Now reads 5, 3, 4, 1, 2. So 5, 3, 4, 1, 2. So we've not just created this max heap structure from the unsorted array, which was over here. So we now turned this into this. We haven't really made any swaps. So because this is just happening now. So here we haven't really changed anything about the array, even though it looks like this, but this is just how the computer is going to think about this array up here. And now the actual heap sort algorithm is not too hard. What heap sort is now going to do, it's going to swap the first and the last element. So it's going to swap this 5 and this 2. And now it's going to lock in this 2, add this 5 at the very end. Why is that? Well, heap sort now knows that 5 is larger than anything else within that array, okay? Because in the binary tree, where every parent is older than their children, by definition, the root node must have the oldest age, okay? It's oldest, so it has the largest value. So we're gonna put this at the very end, and this locking in, so 5 is locked in. I'm gonna denote that using these 2 vertical bars here. So in the future, heap sort is not going to care about this element here anymore because it's already sorted. And well, after we swap that and lock that in the last position, 2 now moved to the very front, and 2 is now the new root, and now we have to what's called sift this down. So we now look at this array here, and we now have to check whether our constraint of the parents being older than the children is still satisfied. Now, the first thing, if we now read this as a tree once more, it now reads 2, 3, 4, 1, 5, and it's structured like this. We can see that this 3 is older than that 5. And by itself, this would be a problem. But since 5 is already locked in, we don't bother about this anymore. So we don't compare 5 with anything anymore. So it's really just about this 3 and this 1, and this is perfectly fine. And so we can ignore that. So we now move up one level, and this is what I got confused before. So the max heap, we always start at the top, but with the sift down function, we start at the bottom. So we are now moving up, and we can see, okay, this 3 and this 2 are out of order. 3 is greater than 2, even though it's currently its child. So we got to make a swap here. But before we do that, the sift down function will check everything within the tree. So it will not make the swap right away. It's also going to look at this 2 and this 4, which is the same problem. So it's not going to pick that 4 and move that up. So it's not going to make the swap right away, but it's going through all possible swaps and then make the last one, okay? So it's not going to look at this. So it's moving now up this 4, and the tree now reads 4, 3, 2, 1, and 5, which if we write it in our typical array form looks like this: 4, 3, 2, 1, and 5. And now we are again swapping the first and the last element. And this pattern will now repeat over and over again. We first create the max heap, and then we are swapping, sifting down, swapping, sifting down, and so on. Okay, so anyway, where were we? We were here. Swap first and last element. So I'm going to swap this 4 with And now, since 5 is already locked in, we are not looking at this 5 anymore, but this is now the last element in the array, this 1. So we are swapping 4 and 1. 1 now is now the new root, and 4 is now also locked in. So we now have 2 elements already locked in. 4 is locked in, and 1 is the new root. Now we're going to start the sift down process once more. We're going to look at this tree. Well, don't bother with this down here. 4 and 5 are already locked in. We look at this and we realize 3 is less than 1. And 3 is greater than 1, and 2 is greater than 1. So we're going to move up this 3 because it's the greatest element. Okay, so it's going to first check all of this, but 3 is the greatest. So 3 goes up here. The array now reads 3, 1, 2, 4, 5. We again have to swap first and last element. We are swapping 3 and 2. This is now what we are going to be doing. So we swap this, 2 and 3. 3 is now also going to be locked in, and 2 is now the new root. We'll look at this. We are sifting this down, but there's nothing to be done here really because 2 is already greater than 1. So we can just spell it out like this. There is no additional step involved. And now we're swapping first and last element, which in this case is now 2 and 1. Everything else is already locked into place. And now we just have this 1 left because 2 is now also locked in. And yeah, this is now the final tree. Everything is already locked in. So yeah, this is it. This is now the final array. And this is how this process works. So in a way, it's imposing some structure from the beginning to the entirety of the array, which is something that binary insertion sort had not done. Binary insertion sort only worked with the fact that the sorted section is sorted and it could make efficient use of that. But here we are imposing this max heap structure onto the entire array before we go through the actual sifting down and swapping part. Okay, I think that's it for the numerical example. Now it's time to get coding. Okay, so we'll have to code 3 functions. The first one will be the sift down function. So this function will be essential and it will be called over and over again. Then we'll also code a function that I'll call heapify. And this function, that's what's happening at the beginning of the array, where we're creating the max heap. So this is what I'm going to be calling heapify. And this sift down function, that's what's going to be called over and over again. And then lastly, well, we have to have the actual function, the wrapper function, so to speak, that puts everything together. And this will now be simply the heap sort function. I guess you guessed that name already. So I'm just going to make this a pass. And now we'll start with the sift down function. Now the sift down function, it has to have a bunch of parameters. The first one is the array itself, and then it has to know where to start, where to end. So that's kind of just like marking which sections of the array are not already locked in, because you don't have to bother with those. Okay, and yeah, so let's get started. So we'll first define our root, which will be at first our start, and now we'll have a while loop. And well, what's it going to do? It's going to store the children, and initialize the swap. Okay, or initialize swap. I'm just gonna, initialize swap. So we're going to store the location of the left child, and this is just 2 times the root plus 1. So let's look at this. If we had this tree, 1, 2, 3, 4, 5, and say 1 is the root, obviously, then how do I get this location? Well, this is index 0, so I'm taking 2 times 0 plus 1. It's going to be index 1. So here, index 1 is the left child. But had we been looking at this down here, this would have also worked. So if we had just been looking at the subtree here with 2, 4, and 5, it's this element, and this. Now 2 has index 1. So 2 times 1 is 2, plus 1, that's index 3. So 0, 1, 2, 3 in the Python indexing will then give us this 4 as the left child of 2. Okay, so this is where this little equation comes from. Now the right child, that's obviously a lot easier given the index of the left child. Well, here we'll just have to say left child plus 1, and that's it. And now we'll have to initialize which of the elements we're going to have to swap. And at first, we'll just set this to root, okay? And now we have to update the swap. So we'll now have to update the swap if the left child actually exists. So that's important because it could be non-existent. Swap of the left child, update the swap if the left child exists and is greater than the root. So that's an important condition here as well. So if the left child is less or equal than end, so this is just checking whether we are actually within the part of the array that we are looking at, if the left child is actually within that part of the array, because remember, this is just an equation and it can go out of bounds, so to speak, because we are not checking with end here whether or not we are exceeding that. Okay, this is why we have to have this condition in here. So now we'll have to have an end here, and now we'll just checking whether not the position, but the actual array element, so the array at index position left child, whether or not this is greater than a swap, okay? So here I wrote root because right now swap is equal to root, but just to be clear, then I'm just gonna call this then the current swap, okay? So this is important. And well, if that is the case, we'll update this. So swap is now equal to left child. We have found a new element which needs to be swapped. And now we'll repeat this pattern once more for the right-hand side child. Okay, so now we'll update the swap if the right child exists, and now comes the end part, and is greater than the current swap. So this is important. And yeah, now we'll have to change this to right child. And now I'm going to copy this over here. So again, we're checking whether or not it's actually less or equal to the end of the section of the array that we're looking at, and if the right-hand side child is greater, or not the index location, remember, but the actual array element, the actual child is greater than the current swap. And if that is the case, we'll swap this down here. Haha, we're swapping the swap. Okay, and now we'll actually make the swap. Okay, so if the swap is not equal to the root, well, here we're now going to change the root. So a root, a swap, you know that pattern from before, is equal to the same two things, except they are now reversed in order. Okay, and now we'll have to update this. So root is now equal to swap, and I think I'll have to indent this in the first place. And if the swap is not equal to the root, there's nothing to be done here. We can just return out of this. Okay, now we have to think about yielding. So here, I'm thinking I'm going to be yielding up here before we're actually making the swap. So we'll yield A. And for now, I'm not going to put anything into this. We'll worry about the colors later on. So this is it for the sift down part. And now comes the heapify part. Don't worry, we already managed to code most of the tricky part here, okay?